In this video, we'll be seeing how to represent the equation of a line using a vector. We already know that one representation of the equation of a straight line is the familiar y equal to mx plus c, where m is the gradient of the line and c is the vertical intercept. There are other representations as well, like y minus y1 equal to m times x minus x1, where m is again the slope and x1, y1 is a point on the line. Both of these are pretty much equivalent and can be rearranged into each other. But another thing we can do is to parameterize a vector and use this to represent a line. Essentially to create a vector which varies with some parameter, a vector function if you like. This can be useful in a lot of physical applications, for example linear trajectories of particles or objects. And it can be extended into non-linear functions to represent non-linear trajectories of particles. Here we're going to see how to construct such an equation given various different types of information. The first of these is where we're given 2 points, A and B, and asked to construct the equation of the straight line that passes through both of these points. In the box we're shown that r of t, some vector r parameterized by a parameter t, is the equation of the dotted line through A and B. And it's given by the position vector of A plus the parameter t multiplied by the displacement vector from A to B, where t can vary from minus infinity to infinity. This is how we write the equation of the straight line in vector form, but how does this equation come about? To see how it works, let's just have a look at a few of the possible infinite number of parameter values. When t is equal to 0, r, our vector of 0, is equal to OA plus 0. So we have just the position vector of A. In other words, r points directly at A. When t is 1, we have OA plus 1 times AB. So r of 1 is OA plus AB. In other words, O to A and then A to B. So our r of 1 vector points in this direction. When t is minus 1, we're going to end up in the opposite direction, O to A and then minus AB. So we'd end up here and then back down here somewhere. So something roughly like this. Now imagine if this dotted line kept on going back in the other direction, as it probably should. And it should go on in this direction as well. Each one of these vectors that we've just calculated points to a point on the dotted line. In fact, if we did that for any t value at all, t equals 2, t equals 12, t equals a half, t equals minus 0.1, any value at all that we like, we'd come up with a vector r which would be somewhere along that dotted line. When we take all of those vectors together, we end up pointing at every single possible point along that line. So as t varies from minus infinity to infinity, we generate all of the points on the line. And so our vector equation here in the box gives us the vector equation of the straight line that passes through A and B. In the example here, we're asked to construct the vector equation of the straight line through the points minus 1, 1.5, and 3, 3. Sketch the line then and show the position vectors r0, r of 1, and r of 0.5. Pause the video now for a few seconds and have a go at this one yourself. To find our equation, we're going to need the OA vector and the AB displacement vector. So I've let A be the first given point and B be the second. So then OA is simply minus I plus 1.5j, and A to B is going to be 3 minus minus 1, or 4i. 3 minus 1.5 gives us plus 1.5j. Then we can substitute those into the formula for the equation for the line. R of t is OA, or minus I plus 1.5j, plus t times the displacement vector AB. So t times 4i plus 1.5j. Finally, we can rewrite this in a form of ij vector form. So we're going to put the i's together and get 4t minus 1 in the I direction and 1.5t plus 1.5 in the j direction. The position vectors r0, r of 1 and r of 0.5 can then be evaluated by simply substituting for the value of t. So r of 0 will be 0 minus 1i, or minus I, and 0 plus 1.5j, so plus 1.5j. And in a similar way, we have r of 1 is 3i plus 3j, and r of 0.5 is equal to I plus 2.5j. You can see the sketch of the line already drawn in black. We can do that without this vector equation. But now we can also plot on there these position vectors, r of 0, r of 1, and r of 0.5 to check that we've got everything okay. Now r of 0 should simply be from origin to A, and we can see that we've moved back 1 in the I direction and up 1.5 in the j direction. And so that one's correct. We can see it pointing directly at A. R of 1 should be when we're moving from O to A and then A to B. Because the parameter t is 1, we're just adding one lot of AB to the end. And we can see that it does indeed point to 3i and 3j. Finally, R of 0.5 takes us across 1 and up 2.25. And we can see that that's indeed the case, that the line is approximately at 2.25, give or take a little error from the sketch. So there we have our three position vectors drawn on the line. And that's vector equation of a line given 2 points that the line has to pass through. Now let's have a look at the vector equation of a line through a point which is parallel to some other vector b. Given this information, we can see in the box that the vector equation of the line, r of t, will be given by the position vector for the point A plus the parameter t multiplied by the vector we need to be parallel to, or b. And again, the parameter varies from minus infinity to generate all points on the line. But why is this one different in the second term? Why is it tb when before we had t from A to B? Well, it turns out it's actually quite similar. In the diagram, we can see a vector b down here and our point A up here, which we want our black dotted line to be parallel to this vector b down the bottom. Vectors can be translated in space and not really change at all. So we can see b moving up here and still being the b vector. Eventually, it will be lying on the line here, just like the AB vector in our original vector equation of the line formula. So all we need to do then is just take different quantities or multiples of the b vector to generate all the points along the line. When t is positive, we generate the points to the right of A, and when t is negative, we generate the points to the left, moving on as far as we need to out towards minus infinity. So let's check out an example of this formula in action. We need to construct the vector equation of the straight line that passes through the point minus 1, 2, parallel to the vector I plus j. Sketch that line and show the position vectors r0 and r1. So here we have the point A, minus 1 and 2, and our vector B is equal to I plus j. Stop the video now if you like and have a go at this one yourself. In this example, we're given everything we need, so we can just go back to the formula, r of t is OA plus TB, and substitute in what we need, O to A being minus I plus 2j, and the B vector being I plus j, remembering that t is between minus infinity and infinity. This generates all of the points on the line that we need. We're asked to show r of 0 and r of 1, so we can calculate those easily by substituting in the t value of 0 to give us simply minus I plus 2j, the position vector of A, and r of 1 by substituting in a t value of 1. So we have minus I plus an I gives us 0 i's, and 2j plus 1j giving us 3 j's. And those are the two vectors we're asked for. Now we can also sketch the line and show those vectors on that graph. So on our graph here we can see the point A at minus 1 and 2, the vector B which goes from the origin to I plus j, and then our straight line which is parallel to B. The two vectors that we've just been asked to find we can also add in, with r of 0 simply being the position vector of A, and r of 1 just going vertically upwards here to 3. So there we have another example, a different way of finding the vector equation of the line when we're given different information. So now you've got two ways of writing a vector equation of a line, one where it passes through 2 points, and one where it passes through a point and a vector that you're provided with. If you're looking in other texts, as usual, check out any section that introduces vector equations of lines. If you want to look at something a little trickier, look into the vector equation of a plane. Attempt the exercises from this worksheet and make sure that you're noting down anything that you need to get help with.